You already know that an ellipse is the set of all the points in a plane, the sum of whose distances from two fixed points is constant. You have also learnt about the various parts of an ellipse, like its two foci, two vertices, center, major axis, and minor axis. You also derived the relationship c square is equal to a square minus b square, where c is the distance of a focus from the center, a is the length of the semi-major axis, and b is the length of the semi-minor axis of an ellipse. Now let us look at another important relationship in an ellipse. Let k be the constant equal to the sum of the distances of any point on the ellipse from its foci. Since vertex A lies on the ellipse, the sum of distances AF1 and AF2 is also equal to k. Let this be equation 1. Now, AF1 is equal to AO minus F10, or the length of the semi-major axis A minus distance c of focus F1 from the center. AF2 is equal to AO plus OF2, or the length of the semi-major axis A plus distance c of the focus F2 from the center. Substituting the values of AF1 and AF2 in equation 1, we get k is equal to 2a. What is true for vertex A is true for all the points lying on the ellipse. Thus, the sum of the distances of any point on an ellipse from its foci is equal to the length of the major axis, or 2 times the semi-major axis of the ellipse. Eccentricity is another important concept associated with all conic sections. It is a measure of the deviation of a conic section from being a circle. The eccentricity of an ellipse is denoted by E and is equal to the ratio of the distance of a focus from the center to the length of the semi-major axis of the ellipse. Squaring both the sides of the formula for eccentricity and simplifying, we get b square is equal to a square into 1 minus e square. Remember this formula as it comes handy in solving many problems. Let us now derive some standard equations that are satisfied by all the points lying on an ellipse. If we consider an ellipse with its vertex at the origin and its major axis along the x or the y axis, then there are 2 distinct possibilities. The first possibility is that an ellipse has its center at the origin and its major axis along the x-axis. In this case, the foci of the ellipse lie on the x-axis. The second possibility is that an ellipse has its center lying at the origin and its major axis along the y-axis. In this case, the foci of the ellipse lies on the y-axis. Let us derive an equation of the ellipse for case 1 with its center at the origin, the major axis along the x-axis and the foci at minus c, 0 and c, 0 on the x-axis. Consider a point P on the ellipse with the coordinates x, y. The sum of the distances PF1 and PF2 is equal to 2a. Let this be equation 1. We already know the formula for calculating distance between 2 given points. Using the distance formula, we get distance PF1 is equal to under root x plus c whole square plus y square. Similarly, using the distance formula, we get distance PF2 is equal to under root x minus c whole square plus y square. Let us substitute the values of PF1 and PF2 from equations 2 and 3 in equation 1. Rearrange the equation. Square both the sides of the equation. On simplifying, we get under root x minus c whole square plus y square is equal to a minus c upon ax. Squaring both the sides again and simplifying further, we get equation 4. Substituting the values of a square minus c square as b square in equation 4 and simplifying further, we get x squared upon a square plus y square upon b square is equal to 1. We can say that equation 5 represents the given ellipse if the coordinates of point P as derived from this equation satisfy the geometrical condition PF1 plus PF2 is equal to 2a. From equation 5, we get y square is equal to b square into 1 minus x square upon a square. Substituting the value of y square from equation 5 in equation 2 and simplifying, we get PF1 is equal to a plus c upon a into x. Substituting the value of y square from equation 5 in equation 3 and simplifying, we get PF2 is equal to a minus c upon ax. Substituting these values of PF1 and PF2 in equation 1, we see that the geometric condition is true. Thus we can say that point P lies on the ellipse represented by equation 5. The equation x squared upon a square plus y squared upon b square is equal to 1 is the standard equation for an ellipse with its center lying at the origin and the major axis lying along the x-axis. Similarly, we can derive the standard equation for an ellipse with its center at the origin and the major axis along the y-axis as x squared upon b square plus y squared upon a square is equal to 1. These two equations are called the standard equations of an ellipse having its center at the origin and the major axis along the x or the y-axis. Here, we can make some interesting observations. In an ellipse, the length of the major axis is always greater than the length of the minor axis. Thus we can say that if the denominator of the x squared term is greater than the denominator of the y squared term, then the major axis of the ellipse lies along the x-axis. Similarly, if the denominator of the y squared term is greater than the denominator of the x squared term, then the major axis of the ellipse lies along the y-axis. Note that both the standard equations of an ellipse contain even powers of x and y. Therefore, an ellipse with its center at the origin and the major axis along either the x or y-axis is symmetrical about both the coordinate axes. What this means is that if a point px, y lies on the ellipse, then the points minus x, y, x, minus y, and minus x, minus y also lie on the ellipse. A line segment passing through the focus and perpendicular to the major axis with its endpoints lying on the curve of an ellipse is called the lattice rectum of the ellipse. Since an ellipse has two foci, it has two lattice recta. Lattice recta is the plural for lattice rectum. Consider an ellipse with its center at the origin and the major axis along the x-axis and lattice recta AB and CD. Let the length AF2 be L. If C is the distance of focus F2 from center O, the coordinates of point A are C, L. Recall the standard equation of the ellipse with its center at the origin and the major axis along the x-axis. Since point A lies on the ellipse, its coordinates must satisfy the standard equation of the ellipse. Substituting the coordinates of point A in the standard equation of the ellipse and simplifying, we get L is equal to b squared upon A. Since the ellipse is symmetrical about the x-axis, distance AF2 is equal to distance F2b. Hence, the total distance AB is equal to 2b squared upon A. Distance AB is the length of the lattice rectum. Thus, the lattice rectum of an ellipse with the semi-major axis equal to A and the semi-minor axis equal to B is given by 2b squared upon A.